a little bit about the general ways that ATP is made, and that is in the chloroplast and the mitochondria, they're made basically by the same thing, which is ATP synthase. And what we're just going to be covering very quickly are some general concepts that you've probably already had in physics. And the point is that once we have something that's biology, i.e. we have a living system, then the laws of physics of course apply, but systems have evolved to sort of take advantage of the laws and do some things that would otherwise not be possible. So the big thing about the difference between biochemistry and chemistry is with biochemistry you've got information molecules involved, and everything that's made is made to work together, so it's not a test tube. You know, it has a cell membrane. It has a lot of organization to it. And probably the most advanced feature that we have in cells is the way that ATP is made. And it's the chemiosmotic, and we've mentioned it before, and we're going to talk about that today. And we have this area of physics called bioenergetics, which is again biology, the physics of living systems. And we all know there are two kinds of, well, there's more than two kinds, but there are basically two kinds of strategies. Photoautotropes are plants, higher plants, where they basically get almost, if not 100% of their actual energy from sunlight, which is, we talked a little bit about that last time, and of course we're going to talk a lot more about it today or our next lecture. And then chemoheterotropes, chemoautotropes, there's a whole bunch of them. You know, that's what we are, is that we have the ability to take carbon, eat it or absorb it or whatever, and we can take that absorbed carbon and by a series of reactions we can oxidize that carbon and use it to do things, to make energy, to do things, okay? So, you know, we can't live by just sitting outside and getting a suntan. Now, you all know about thermodynamics. And then on the top of thermodynamics, once you, and I'll say add a cell membrane or add something that is considered to be live, then is we change what we're looking at. Because we're looking at incredibly complex systems. So when your muscle moves, there's all sorts of reactions occur. Whenever your muscle moves, you are breaking down a tremendous amount of ATP. And you're making ATP. You know, I think I've told you, we have about a 5-second to 10-second supply of ATP in our bodies at any given time. And every time your muscle moves, every time you breathe, most reactions require ATP. Now, the first law is the law of conservation of energy. And this, guys, remember, it means that energy is real and that we can transform energy, but we can't do away with it and we can't make energy. You know, there's never going to be a perpetual motion machine where you actually get more energy out of a system than you put in. If we talk about biology, we're talking about we are incredibly efficient in terms of what we can do with the chemicals. And we also have the fact that in almost every reaction, some energy is going to be lost as heat or something else. Now, this is something that a lot of ecologists talk about, and that's entropy. And everything basically is going to randomness. And if you're interested in ecology, a lot of times that you'll go and you'll look at a crop. Okay, that crop, if you're planting a crop, and it's not a true level of entropy, but the level of entropy is lower. And if you take that land and you don't do anything, what happens over time? What happens to the land over time? So we had a crop planted out here. If I don't do anything, what happens next year? Yeah. And if we don't do anything to it, over time, you're going to get different kinds of weeds come in, different kinds of plants. Then that's going to cause different kinds of plants to come in. And so from an ecological standpoint, you can say the entropy, the organization is decreasing. You're going from a row of crop plants to random plants. And so you're putting more entropy into the system. Now that's not a true, not genetic, physical type of entropy, but it's something that makes sense. So if I want to keep a piece of land as a row crop, I'm going to have to plant it every year probably. So I'm going to have to put energy into the system. And so that goes from that kind all the way down to our cells have less entropy than if we take the cell and take the cell membrane off. Okay? So our organization is the opposite of entropy, and the more organization, the less entropy. So this requires energy. That's why we need to eat. Now, don't worry about the equation, but you've heard of Gibbs free energy, which is a description of how energy is used. And the thing here is G is how much energy is available to do work. And work is real. It's a measured energy, and energy is real. Energy is everything we do. And from this equation, you can see what part is heat and what part is entropy. Now, there are two kinds of reactions that occur. Exergonic, and that's a reaction that occurs without you having to add a catalyst to it. And usually those reactions will give off some heat. And I can't think of many you would do around home. Well, I tell you what, there is a reaction that's very common. Anybody ever get some soap, some powder, washing powder, hold it in your hand when you add water to it? Your hand will actually, it heats up. The actual solubility of the part of the base, that is what is the powder, as it's solubilized, it actually gives off some heat. So you don't have to have anything to keep that reaction from happening. The other kind of reactions are endergonic, and that's what most of the synthesis reactions are in cells. We have to put energy in to get things made. Okay? And the main thing that these cells use, plant cells, bacteria cells, human cells use to move energy and to store energy, as you all know, is ATP. Very few organisms use anything but ATP. And so the reason why we have to consume carbon is to make ATP. And a lot of reactions require ATP to occur. Now, let me show you what I mean by this. We have a reaction here which occurs and releases delta G is minus 32. So when ATP is hydrolyzed, there's a release of energy. Okay? If we take a reaction glucose plus phosphate to produce glucose 6-phosphate, which by the way probably wouldn't happen, to get this reaction to occur by itself is we have to add energy to it. Okay? So if I have glucose and phosphate floating around in a beaker, to get the glucose and the phosphate to bond together is going to require a lot of energy to be put into that system. And then it's not going to happen that often anyway. And then the bottom line there is what cells do. We take ATP and glucose and we use that energy hydrolysis to put the phosphate onto glucose, and we actually get a negative amount of energy. So this occurs easily. And when you think about photosynthesis, and even more when you think about metabolism, you all know what glycolysis is. You all know what the citric acid or the TCA cycle is. And what has evolved are all these little tiny steps. You know, each little step in the pathway has evolved to minimize the amount of energy you have to put in, and for some of the reactions to maximize the amount of energy that comes out. So when we talk about photosynthesis, we have that summary equation that is one line, but in biology it's not done that way. We take that one line, that one equation, and we break it down to 100 steps and move electrons around in such a way as to maximize the energy we get out of the system. So it's a different way of thinking, you know. And this is how things work. Almost everything, every reaction, in metabolism especially, is a series of oxidation and reduction reactions. We're moving electrons around. When light is harvested, we're moving electrons around. We're taking the photons, and at some point that photon becomes an electron, and it oxidizes and reduces and reduces and oxidizes until it gets to a point of where it's in a product, a molecule, a compound that's stable enough to exist inside the cell. And you probably remember from general chemistry redox, which is really complex. And we can look at some things that are, look at a couple of molecules, and we can determine what's going to happen, which one's going to be reduced, which one's going to be oxidized. And when we talk about photosynthesis, we're going to talk about how something that is really stable, water, can be forced to become oxidized. And that's where oxygen comes from, right? Oxygen in photosynthesis is a useless byproduct. It has nothing to do, the product is useless. It has nothing to do with moving energy around. The only thing water does is provide electrons to get photosynthesis started. And we're not going to talk about couplet or the other kind of reactions. And I want to finish up a little bit with how all this happens to produce ATP. And that is the chemiosmotic hypothesis. And one part of this hypothesis is that membranes are fairly impermeable to protons. And the second part is there must be carriers, and what's in a membrane that's a carrier, it's a protein or series of proteins that must be embedded in the membrane to carry the protons, and we are carrying protons, we're also carrying electrons. Electrons and protons move together. Okay? In plants, it's the chloroplast and mitochondria. They're double membrane bound. You've seen these before. Here's a picture of where the light reactions actually occur, which we're going to be talking about. And you remember they have these different structures. Oops. The S is the stroma, and this is something we're going to be talking about next week. These are where the dark reactions occur in the soup inside here. And then in the grana, if you remember, that's where the light is actually harvested. So the light's coming in here or in this way, and it's actually being harvested here. So where we have the electrons stored is in here, and then these stored electrons are finally used out here to produce glucose. You remember these terms that we had? And in the stroma, we have an enzyme we're going to talk about called ribisco. This is the enzyme that actually grabs CO2 and fixes it into carbohydrate. This is the most common protein in the world. So it is the #1 protein in the world. And every leaf is just chock full of ribisco. And here's the diagram of the chloroplast. We're going to be talking about what happens here that ends up happening in the lumen and then ends up happening, taking those electrons into the stroma. I like to say again, like if you squint your eyes and look at a mitochondria, it looks a lot like a chloroplast, double membrane bound. It has an outer and inner membrane, the cristae, you remember, and the matrix. The cristae is where the ATP is made, and the matrix is where the TCA cycle occurs. Same thing you've seen before. Here's a micrograph of the mitochondria. So they probably came from the same place. And both of these really distinct organelles make ATP the same way. And the protein they use is a protein called ATP synthase. Okay? And this is what it looks like. Now, this is a machine that is embedded in the membranes of the mitochondria and the chloroplast. And I linked to an actual, let's see if I can call that up. Oh, and I don't think you're going to be able to see this. I'll have to link this. I don't think you can see this. I'll link this. And what I wanted to point out here is this thing moves. And as protons flow in, the protons actually cause this thing to spin around literally. And as it does, then the ratchet here, look at this. As this after 3 protons or X number of protons, it moves, you have a ATP made. This is a motor. This is the smallest motor that we know. And believe me, there are a lot of people that are okay. So this is the motor, and it's sort of been worked out that for every protons that are moved through here, through this machine, which causes this part to spin around, then we have an ATP made. So we have actually worked out how many protons are needed to cause this machine to move and to produce ATP. So the chloroplast and the mitochondria have the same ATPase. They're slightly different molecularly, but they do the same thing. Okay? If we take this motor and we look at it more in terms of what we're going to be talking about, and here we have a chloroplast with the stroma and the lumen side, is that there are a series of these redox carriers, oxidation reduction reactions, complexes that move electrons around. And as the electrons are moved around, the protons are channeled onto one side of the membrane. And if you remember, when we talked about this before, I talked about the fact that if one side is positive, then the other side is negative. So by moving protons into the intermembrane space, we create this electronegative force that can be used by channeling the protons through this machine to produce enough energy to drive the formation of ATP. Questions? Questions? Okay, and this is called photophosphorylation or oxidative phosphorylation, which is misspelled, isn't it? Both ways, one uses energy from light, so you're taking electrons. If we move back here, we're taking electrons that you have a photon turned into an electron, and then the electron ends up driving this, okay? So those electrons from the photons are converted into stored electrons, and finally it ends up as ATP. That's one of the things that we need from the light reactions, okay? So the electrons then enter into another compound. Any questions about that? God, everybody looks sleepy. I don't know why. Okay. I'll start the light reactions next time, so let's go ahead and finish here. Any questions? Anything? Okay. I'll see you then on Friday.